All right, just a quick update video here. This is unedited. I'm just going to get this out there because I want to share it with you. Several of you very generous viewers have so graciously shared your intelligence in order to supplement my lack thereof. So here's where we are. A couple of changes that I made at your suggestions. Thank you all. You know who you are. One of you really, really knows vacuum tube theory much more than I ever will. And you kindly shared a huge paragraph with some really good information. I think you deleted your comment because I went to look through it again and I noticed it wasn't there. And I'll tell you what, I really appreciate it though. Thank you for sharing. So anyway, I removed these capacitors here. Now, in solid state gear, you always have to worry about Miller capacitance and you have to worry about high frequency oscillations and things like that. And it's just kind of a good practice to put those things there. But vacuum tubes really don't translate to solid state that well. And there's a lot of little nuances about vacuum tube theory that I don't know. So I made some errors in my design. So I removed those because really the determining factor, and how an amp's going to perform when it comes to phase shift and frequency response and so forth, there's always going to be one part of the amp that's going to be the weak link in the chain. We call that the dominant pole. And in a vacuum tube amplifier, it's almost always going to be the output transformer. And as such, you really don't want to clamp the other nodes of the amplifier down below where this is. The other thing is when you're dealing with negative feedback in this type of amplifier, you might think it's not important for this to operate above audio frequencies, but actually because of the loop delay and so forth, and if I'm explaining this wrong, please correct me in the comments, and those of you read it so you can see the correction. But essentially there's a delay in this, which can cause phase shift and so forth. And what happens is if you filter this too much, or if you clamp it down too much frequency-wise, the feedback can't work the way that it's intended to. So really, a rule of thumb that's used, I found out, is anywhere from 10 to 20 times the max frequency of your dominant pole, which is this transformer, is what you need for this whole loop to work properly. So in other words, if you want this to work at 25, 30 kilohertz, to get your maximum frequency response, this needs to be able to operate at 10 to 20 times that much. So you're upwards in the megahertz range of frequency response that this front end has to have. And by putting those caps in there, that limits that. So I know that sounds strange. Why do I need a 1 megahertz preamp to drive a 20 kilohertz signal? It's because of the way the loop works and so forth. So I hope I explained that right. So there's a couple changes I made there. Some other things I did was I made a few small changes to the current source, and I actually mocked one up here on a board and I tested it and it works perfectly. And this I had at 1.6K, but really that wasn't where it needed to be. I think it's going to be closer to 1K to get our 6 milliamp that we need there. The other thing I had to do was I had to adjust the midpoint here to bring this voltage more in its middle of its swing. And again, this is stuff that you guys mentioned, and you're right. My thought and my understanding of how these Cascodes worked was different than how they actually do work. Again, I've never worked with vacuum tube Cascode circuits. This is not something that, and then when you add to it a constant current source, a lot of things affect it. And if you really don't understand how it works, it's really easy to kind of go the wrong direction with your design. That's what I did. So really it was some simple fixes though. Remove these caps, remove those two caps on the, between the screen tap and the anode on the output. And I also had to change this divider here. So if you look now, I now have a much lower resistor here. It's only 162K. And then down here, I bypassed it with this capacitor. Now, some of this stuff is me reading more about it. Some of it was taking advice from some of the comments. And some of it I actually went back and referred to AI. Sometimes when the RI isn't working right, you can get a little bit of guidance from AI, although it makes as many or more mistakes than the RI does sometimes. So just keep that in mind. Don't think that you're going to go on the internet and type in design me, you fill in the blank, any circuit or any kind of thing, and have it perfectly tell you everything, because there's so many variables. It's a computer, and there's variables that invariably, no pun intended, you don't put into your questions and things. So it's not able to make the correct calculations based upon, I mean, even though it's speaking to you in the vernacular and you think that it's some kind of person on the other side of that computer, it's a computer and it only does what you tell it. My mother always used to say that. She was a computer programmer for her career. And she said, a computer will do exactly what you tell it and nothing else. And that's how it works. So anyway, I did use a little bit of that and did get some number crunching, and we came up, this is where I came up with. And I think this is going to work. It's to the point where I think as far as the topology is concerned, this will be good, and I will be able to build it, and then just swapping out a resistor here and there if I need to tweak it, because nothing ever goes as you calculate. That'll be easy. Now the other thing I did was I changed the power supply a little bit. First of all, this 300 volt line was just an actual resistive dropper circuit. And that would have worked as long as everything is running perfectly within its parameters. But if anything changes, so in other words, if the amount of current required by the front end of the amp changes or anything, the voltages are going to drop. So it's not going to, in most tube circuits, we don't care about that because plus or minus a few volts really doesn't affect the way the tubes work. But remember, we're dealing with this, and we're dealing with constant current source, and changes in voltage here will make a difference. So you kind of want to make that a little more stable power supply. So the first thing I did was I didn't want to have so much resistance in here that everything was being bled down to heat. Because it basically, a resistor just takes whatever energy that goes into it and converts it to heat. And so basically you're wasting so much power that way. So by using a reactor, it makes it more efficient. Now here's the thing. The way it was configured before, this really wasn't being used as an actual choke. It was being used more like a filter, a noise filter. So low frequency noises and so forth, it was a low pass filter. Now it is actually being used as a choke. And in order to do that, you can't have a regulated or filtered supply feeding it. It needs that ripple for it to do its thing. And so as a result, I had to put this isolation diode in here so that the inductor can be an inductor. And now that still doesn't matter though when you're talking about DC current. And this is where all this got really confusing to me. I had to really kind of research this. From a DC standpoint, this thing has a copper coil resistance of 224 ohms. And of course, we're going to use that in conjunction with the 10K 10 watt resistor. And the values of these are going to be determined by the requirements of our regulator. And this is just a very, very basic series regulator. it's using two 150 volt 5 watt Zener diodes, and they need to be 5 watts because when the tubes aren't warmed up and this thing's not drawing current yet, all of that current's going to go into these here. So they're going to be dissipating maybe about 3 watts or so just for a little while. So if you put a half watt or even a 1 watt diode in there, you're going to be stressing them out. So you need a 5 watt Zener. Those are readily available. So there's all kinds of math that goes into calculating this, but really you can't just think about the current going to here, because really the current path, you have to have this transistor. I'm using a big high voltage transistor. High voltage transistors that can dissipate high amounts of power don't usually have much gain. This one, for instance, only has a typical gain, or typical HFE, of 15. So what that means is you need a fairly decent amount of base current in order to get the collector to emitter current up to where we need it. Now I'm assuming an average load of about 25 milliamps, because it's not going to be that much, but it's going to be somewhere around there to drive the cathode followers and this front end circuit, the differential circuit. So you're going to need a total of, I want to be able to comfortably drive a 25 milliamp load. So in order to do that, you need a good bit of current going through these, and that's why these will warm up. If you use like a half watt diode, it's not going to work. It's going to be too much for it. So I'm going to use these 5 watts. I have a bunch of them, or well, I have several of them, enough to do the project. So that's what I'm going to use. And going through all of that, it was really interesting. And I used this AI, and I had it, I just copied what it came up with. And if you want to read through this, I'm not going to read it to you, it'll take too long. But you can see there's the summary of kind of how it works. So there's the bottom. So let me start at the top. I'll let you, pause the video to read it. Then I'll move it down and let you read the bottom part. And I took this note here on the side because this was the most fascinating part of the whole thing, of how the choke works. The choke has what's called a critical current. First of all, they tell you, a choke regulator, they tell you, they always give you this 80 MA. That's the maximum amount of current that we can draw through here and have it still act as a inductor. When you exceed 80 milliamps, it stops acting like an inductor and starts acting like a DC resistor. You start seeing this 224 ohm copper resistance of the windings. So you have to stay anything under 80 milliamps, this thing will work just like a 12 Henry inductor. But here's another thing. This thing also has what's called a critical current. The critical current is a minimum amount of current that it needs to work at also. And so, and again, I didn't really understand a lot of this, but there's actually a formula for calculating it. And here it is right here. And if you look, you see the critical current of an inductor is the DC voltage coming out of the inductor divided by 4 times the angular line frequency, which is this really cool looking average white band record jacket, middle the W. All right, some of you might get that. Times the inductance in henries. And so, of course, we're feeding it with a 60 hertz signal here in the United States. Across the pond, it could be 50 hertz, but it's the same thing. But here's the really cool thing is when you do the math, you come up with 4W equals, or 4, I'll call this W, equals 1508, because 2 pi times that 60 hertz equals 377, and then you times that by 4, you get 1508. And in a perfect sine wave, that's what it would be. But we're using a full wave rectified signal, and the diodes actually have a dropout in them. So it distorts that sine wave, and it's not a perfect sine wave. And I'm sure you have to get into some kind of derivatives or something to figure it out. But basically, the constant becomes 1130 after you factor that in. That's where this number comes from, this 1130. So you see, I critical equals VDC divided by 1130 times the inductance. And I didn't know any of this stuff. This was really cool. So essentially, this is I critical is 26 milliamps. And so as long as we keep a current draw above that, the choke will be working properly. And it calculated that we're at about 30.2 milliamps. And all of this gets really confusing because you have different current loops, not only through, through here, through the base, but you also have current going through here when this thing starts to operate. So 25 milliamps here is not going to be 25 milliamps here. It's going to be a lot more. And that's, I guess, what I'm driving at. And calculating that was what this is all about. The reason this is important is anytime you don't meet those criteria, that 520 volts that's feeding in here is going to go right through here, and it's going to show up over here, and you're going to put a whole ton of voltage across these diodes that they're going to have to drop. And for a short while, you're going to have a much higher current through these diodes, which means they're going to dissipate more wattage. And under that condition, they will dissipate about just under 4 watts, about 3.5 watts, something 3.9, something like that. So that's why you spec this out. So this thing is actually designed to hold together under all conditions. The other thing is I had it run the numbers, and this thing will stay stable from 0 milliamps in here, at the load, clear up to about 65 milliamps, which is way higher than we need. So this will be rock solid. That doesn't mean it's going to be 0 milliamps here. It just means we're not loading it with any more current than the circuit itself draws at idle. Hope that makes sense. So long story short, we have a really quiet, really well filtered, really well designed regulator, until one of you come on and point big flaws. I don't know. And then second of all, I changed this. And I changed this divider so that now that we have a higher voltage here at this midpoint, we need to change our filament elevation. So for the 6SN7, I have that set to about 108 volts. So we're going to elevate these filaments to about 108, and which is well within the heater cathode voltage difference that this thing's rated for. And in this one, I don't want it to be that high, so I took it down to about 96 volts. And these are just regular resistors that I can use, and they don't need to be high wattage because there's no current. It's just a reference. And again, the reason for D9 is because we don't want the chokes to see this capacitance. In other words, these caps cannot bleed backwards through this diode into here and hold this up. That's the purpose of it. We want that ripple voltage to get there so this can do its thing at 60 hertz. So here's the little toroid choke in question, the star of the show here. Here is the power supply transformer. It's huge and really heavy. And I'm ready to start cutting things out. So I'll bring you along for the trip on that. And then when we go to actually solder the parts on the board, we'll do a solder and chat. And who knows where that'll go. So that's it. I just wanted to update you, and thank you again to all of you who contributed to these changes. Take care, everybody. I wish you all peace, joy, happiness, and good health in your lives. Until next time, stay well. Bye-bye.